Hi friends, in this video we'll discuss about dissolving of gas into liquid. So maybe mostly we will see this soda manufacturing in which the gas is dissolved into the liquid, the soda, or any cool drink company also they will try to dissolve the carbon dioxide into the soda or its cool drink. So you can see here this is a bottle what I have taken for a demonstration for purpose. So for example, if this is filled up to this level, and from here, so there is already a liquid present here, and they will try to fill the gas, that is CO2, and when it goes to the manufacturing lane, right, so they will try to apply pressure, they will try to apply high pressure. For cool drinks or sodas, it is commonly it's like 2 atmosphere that would be given to this CO2 gas. So at the high temperature, so the CO2 concentration will reduce in the gas and it increases in the liquid. It means CO2 gas will try to dissolve into the liquid. It goes across the interface and it will dissolve into the liquid. It means CO2 will remain as a gaseous state only, but it is completely dissolved. So it's like the CO2 molecules are now are along with liquid molecules. So I'll keep this a liquid and this is a gas. So gas molecule is all dissolved into the liquid and it is fitted into the gaps of the liquid molecule. So once the gas is dissolved into the liquid, so there is a small formation of carbon dioxide turning into carbonic acid also, if it is liquid, water I mean to say. So CO2 will try to combine with H2O to form H2CO3. This H2CO3 is a carbonic acid, and due to the carbonic acid you will see that fizz nature. Fizz means the small bubbles and the vibrant nature inside the liquid. That is due to the small presence of the carbonic acid. It's not that all the CO2 will be turned into H2CO3, only small amount, right? So now what is the amount of gas that will goes into the liquid is given by the Henry's law. So Henry's law states that at a constant temperature, the amount of gas that dissolves is directly proportional to the partial pressure of the gas that is present above the liquid surface. So the C is the concentration of gas inside the liquid, and that is equals to kH into P. kH is a Henry constant and P is the partial pressure of this liquid, right? And this Henry constant is again a variable with respect to temperature. So the Henry constant is given by Van 't Hoff equation, what you see in the right hand part of the screen. So Van 't Hoff equation is dln of k by dt. So it is d of differential of log k by dt, which is equals to enthalpy change by RT square. So when you try to differentiate and integrate that, you will be getting this equation: log n k2 by k1 equals to delta h naught by r into 1 by t1 minus tt. So maybe I'll take k1 and t1 as my reference values. So k1 is like Henry constant. The reference temperature is like 298.16. So at this temperature, Henry constant for carbon dioxide is 0.033 mole per liter atmosphere. Okay, so this is the unit for Henry constant at 298.16 Kelvin, right? Now at any other temperature, so our any CFD tool should be able to calculate based on this reference temperature and reference Henry constant, and the delta H naught value will be minus 19.2 kilojoule per mole. This is the, it's like exothermic. The heat will be released when the CO2 tries to dissolve into the liquid. Okay, now we'll try to simulate the same process using Ansys Fluent tool, and I'll show you. This is my liquid. So you can see this is a glass solid, and inside this there is a fluid which is a cool drink or any soda or water or anything you can take, right? I'll go to workbench. and I have given a few boundary conditions to it. So this is just a wall what I have taken, and remaining I have left as it is. Okay, so after that I'll go to Fluent with Fluent meshing, drag drop, double click mesh. So I'm using the student version, so it will have only 4 core limitation. I'll be using 3 cores out of it. So the same procedure will be used for bioreactors also. So in the bioreactors, they will impart oxygen or any other gas into the bioreactors, and they will try to have this reaction that will be happening due to the dissolved gases that are present in that, and it will turns into different products whatever is required according to the need. So now I try to, once this is been opened, you select watertight geometry, click on import geometry option, and go to file name, and I'll select all formats. So this is the file. I'll not be adding much local sizing, but there is a portion where a bit refinement is required at the interface, that is given as a name with refine option. So I'll be going to the body size, and I'll just check what is the, so maybe I can go up to 0.8, add local sizing. So to that size or to that portion of that soda or cold drink we're trying to refine there, because that is the interface at which gas will be tried to dissolve into the liquid. Go to generate surface mesh, and I'll be maximum size 2. So curvature and normal angle 30 degrees I'll take. So generate surface mesh. So it has both solid and fluid regions. No, yes, fluid walls to internal. Yes, I want to apply shade topology. Describe geometry. So shade topology means all the nodes connectivity with solid and fluid will be present. And then apply shade topology. Update boundaries, and estimated fluid regions are 3, because top refine and a bottom fluid. This is also fluid, and this is also fluid. So maybe if it is required, I'll just show you what I mean by this. So here this is one, this is bottom one, and this is top one. So everything, all these 3 reagents are combined together as a soda or the fluid, but I have selected this refined portion so that I can have a good mesh at the interface between gas and liquid. So update regions, I don't want to have any boundary layers, because this is doesn't have any flow. It's only demonstration purpose of the dissolution. So I'm not using any of the boundary layers. And then I'll go to generate volume mesh. It is so simple. After the volume mesh is generated, I will show you which portion I have been refined. So you can clearly see here, this is the portion what I've tried to refine, so that interface should exist in this region. Okay, so now switch to solution. Yes. So now it is a transient simulation. I'll activate gravity is also not necessary, because with the high pressures, pressure is only the controlling factor, and we have the multiphase. We'll select volume of fluid and implicit with implicit body force. So these are much more stable parameters what you need to select. Apply, close. Okay, so turn on the energy. Okay, next go to materials, created it. Before that, turn on the species transport, apply. Okay, so you want a mixture, you select mixture template, then go to fluid database, go to fluid, scroll down, select water liquid and carbon dioxide also. Here is the carbon dioxide. Okay, copy, close. Now go to mixer tab, rename it as gas. So I'll take in the gas there will be two constants. One is carbon dioxide and other is air. Remove. And which is more in species, you should be last, right? Carbon dioxide is more for me in this case, so I'll be keeping carbon dioxide as my last species. Overwrite, close it. Okay, then go to this, make it as ideal gas. Now these are all, take it as a mass weighted mixing law, so it will take the next properties as the mass weighted mixing law. Change, create. Now copy this, I'll try to go to materials, copy. So this time I'll make it as a liquid. Go to names, remove, add water liquid. Similarly here water liquid is the more in mass fraction, so that's the reason why I kept it the last. Now this cannot be a ideal gas, so it's a mass weighted mixing law, right? So here this is the mass diffusivity which I have taken a dilute approximation, but you can, if you have the values, you can take that actual value. Right, now go to volume of fluid, and in the phases, first is our gas and second is our liquid. Apply, go to phase interaction and a heat and mass transfer from phase 1, that is from carbon dioxide. So there will be more carbon dioxide present in the gas, and after application of the pressure, so what is the carbon dioxide that has been increased in the liquid? So from phase 1 to phase 2. So and the mechanism is this we should first activate mixture model. Apply, go to phase, and go to species mass transfer. In the species mass transfer, select Henry's law. In that molar concentration, go to Van Hoff, and we have all the reference constants, which is KH, and it is temperature dependency is delta H by R. So delta H is 192,400 divided by R. Because 192,400 is the reason I have converted kilojoule per mole Kelvin to joule per mole Kelvin. And the value is minus 2314. Okay, click OK, and from to zero resistance. So from I'll take a constant value for carbon dioxide. I mean from resistance, what is the value? I've taken some certain resistance, and 2 I'll take it as maybe from it is a zero resistance. So there is no resistance when it is coming from the air, but here two phase there will be some resistance because it's entering into the water phase. So I'll take these values, then approximation values, which you can again refine when you have those exact number, how they vary with respect to any other properties. Right now, go to viscous. I'll turn it into laminar because it's not necessary anyways. We'll not solve the flow equation at all. And now we need to create a region so that we can apply our pressures. Cell region, new region. This I'll take some random values because our, if you go to scale, you can see the values are in Y, which you need to patch. So the minimum is, and I'll go up to minus 0.065, and Z again some random value such that it is out of the scaled values. Now save display. Yes, it is coming up to this refined portion. You can see it's coming up to refined portion such that our interface falls in that refined portion. That is our need. Okay, go to initialization. Now our fraction in carbon dioxide of the liquid is 0, and in the air the fraction of air is 0.1. It means remaining everything is carbon dioxide. The temperature is 300. Now try to initialize. It's taking some time to initialization. So after that you need to patch the gas with high pressure and leave. So what happens to the carbon dioxide content in the water? It should increase according to the Henry's law, right? So what is the percentage with respect to the time, how it is increasing? We can just check in the post processing. So patch the pressure value, maybe I'll take 201,325 for this. Sorry, that previously we need to patch everything with the value 201,325. Initialize. Now everything is with the same pressure. Now we need to remove the pressure here because initially in this liquid there will be no pressure, right? So we need to remove the pressure and make it as 0. So we will try to give 0 pressure to the liquid that is present. So give 0 pressure to this region, patch, and go to phase 2, that is liquid. The volume fraction here is 1. Okay, patch, close. Now go to graphics, counter, right click, new surface plane, make it as an XY plane, create, go to plane and verify the face. So you can see here, you can close this plane, how exactly this looks like. Okay, and you can also check the species of mass fraction of CO2 in phase 2. So in phase 2 there is nothing, the species, because up on the top part there is always no phase 2, but in the bottom part also, even though there is phase 2, but there is no carbon dioxide. So we will just try to run this. Before running, go to controls, in equations you can turn off all this stuff, not required, because we are trying to solve only the species equation with respect to the pressure that we apply. So to run calculation, maybe I'll take as a 0.2 second and I'll give 500 or 5000 time steps. You can just calculate. 100 will be sufficient, I think. And we'll go and save this first. So now we can also do one thing. It is getting saved. After that we can go to solution animations and click this, and after every 10 time steps is active, we can check the result how it is looking like. I'll turn off this, much more pleasing. Okay, so now after running through a few time steps, I'll just show you how the animation is looking like. So you can see, right, so the CO2 is being dissolved and it is going down till to the bottom of the bottle. Okay, and you can also have the view on the different other counters if you require. You can check the fraction in the top part also, because that is used to 0.9. Now it is been reduced. As the time progress, more and more will be reduced. Okay, so hope you have enjoyed the video. Please do like and subscribe. Thank you.